Um, okay, so we start our lecture. Let me share my screen. So can you see my screen or not?
Can, sir.
Okay, thank you. So we are in week number 5. Yeah, this one. Yeah, I want to ask you. You want to have a test on week 7 or week 9? You want to have a test on week 7 or week 9? Mr. Break. もしもし。もしもし。Hello. You
Hello,
want to
sir.
have a week 7 or week 9?
Tak tahu, sir. Mana-mana je.
Mana-mana aja. Okay, can. No problem. So let me know lah. Let's say you want to have a specifically which week, huh? Okay. So we basically in a week 5, and then we actually need to settle already in introduction to electrical machine, and also the drive lah. Especially the basic motor sizing calculation, we should go in already lah for week number 5, so that when you come to the problem-based learning, this one PBL is like a mini project. You will start to use all the software, all the basic, and then all the calculation from here to do your mini project. And then on week 15, you need to submit a mini project report and also the presentation. This time the mini project presentation is quite high. Total is 30 marks. So you need to pay a lot of effort on that. Also, you need to work as a team because you have your own team. I still not yet go look through the lab group yet. Okay, and then hopefully by next week, I think week 7, yes, we will go into the motor winding now. Okay, so now let's have a look on the last week we stopped at how the motor rotate up. Please bear in mind that in order to rotate the motor or generate the motor, we need to have two field. One is attraction or repeller, which means so let's have a look. Let's say I have a north pole and I have a south pole. This one must have an interaction. So this one is attraction. So something like we need to have a two fields. One we call excitation field. One is from the stator field. Okay. One is a static. One is a rotating. Okay. So sometimes we might put like this. This is north, and then south is here, and then we put a north for the stator. Let's say this is stator 1, stator 2, so that one is attracted to there, one is pushed to there. So it will rotate to this direction. Now this is the rotor, this is the stator, stator, rotor part. Okay. So okay. Next. Okay. Rotor poles and motor faces. What is a rotor pole? It's actually the poles on the rotor side. It describes how many magnet polarity exist on the rotor iron. So for example, if let's say we have motor, then the magnet is stick on the rotor surface. This is rotor yoke, or we call rotor steel, rotor steel. Then maybe we have a 4 pole. One is a north pole, south pole, north pole, south pole. So we have a rotor pole 1, rotor pole 2, rotor pole 3, and a rotor pole 4. So we have 4 poles. Then maybe we don't want to have a 4 pole, we can have more less pole. For example, the minimum north and south pole. So this is the one north pole, this is one south pole. So this is the two rotor pole machine. So rotor pole, Okay, close it. So what is rotopole? Rotopole is describe how many magnet polarities exist on the rotor ion. So this is called rotor ion. Rotor ion. Yeah? And then, since the polarity of the magnet must exist in pair, it must exist in pair. It must like pole 1, pole 2. So this one is called two-pole machine. It must be in pair. With the south and the north pole, therefore the number of rotor poles is always even, which means 2, 4, 6, 8. Terminology of P is used for number of rotor poles. Basically, we are not using P, sorry. We are using NP, number of poles. Okay? And then this P, we usually use pole pair. Pole pair maksudnya is NP divided by 2. For example, NP here is 2. Okay? So our pole pair P is NP divided by 2, which is 1. Then, for example, this is NP is 4. 1 pole, 2 pole, 3 pole, and 4 pole. So our pole pair is number of pole divided by 2, which is 4 divided by 2 and become 2. 2 pole pairs. So low speed PM series motor normally have a high pole number, such as this one. For low speed, high speed motor tend to a low pole number, such as 2 or 4 and 6. There is a formula that proves this one later on. For a given rotor speed, number of poles influence switching loss in power electronic converter and iron losses in the stator ion. So what it means is if let's say we know the rotor speed, the number of poles will influence the switching loss. For example, if let's say we want to run this motor, we have a power electronic to run it. Okay, then a lot of switching will go into the motor. Then this motor loss, this number of rotor pole will influence the switching loss. Okay, higher speed, higher losses lower speed, lower losses So as we can learn later in this course, higher pole number means thinner stator back iron and greater output torque for the same current level. This meaning that if let's say we higher pole number means a thinner stator back iron and greater output torque. Higher pole number, which means, for example, now this is a number of pole is a 2. Okay, the stator back iron is iron at the outside one, stator side. Stator back iron, this part. Okay, let's say this is the static area. The width will be bigger than this one. Alright, will be bigger because it will say it's thinner, right? Being thinner. So between higher pole number, the back iron will be thinner. I'm not sure whether I have the figure. Yeah, this one. You see this outside. Maybe I'll put this one now. Okay, so this is called stator back iron, this area. Stator back iron. Okay, this is a stator back iron. Besi kat stator belakang stator. And then this is two-pole machine because we have only north pole and south pole. So just now at the statement saying that if let's say the pole number is bigger, then this will become smaller or thinner. Okay, and then the output torque or output power will be bigger. So if let's say we want to have a high power, then our pole number should be large, and then the stator back iron will be smaller. This is what it is described for one. So on the other hand, more magnet poles mean having less room for each pole and more complexity in the rotor assembly. Yeah. When we want to build a motor with many magnet poles, that will be very difficult. As the number of poles increases, the stated ampere conductor per pole decreases in the inverse proportional. Number of pole increases so that the per unit inductance and synchronous reactance decrease in motors of a higher pole number. A lot of new terms. So let me explain one by one. As the number of a pole increases, so when the number of pole increases, this one, NP from 2 become 10, for example, increases. What is it? The stated ampere conductor per pole decreases. Stated ampere conductor per pole. So stated here. This one is called stated ampere per conductor. Okay. What is it? The stated ampere conductor per pole. Sorry. Stated ampere conductor. Okay. Will be per what? Per pole. Will be decreased. Will be decreased. Is it? Yeah. Okay. Later I explain this one. Maybe I explain. If let's say we focus on here, and then this is the magnet, and then this is our foot. Let's say, let's say like this. This is foot. Although it's a little bit different. Ini dia tak ada gigi. Sini ada gigi. Sini tak ada gigi. So if let's say this number of pole become more, just now it's a two pole, right? If let's say become more, it becomes like this. Or maybe north pole, south pole, north pole, south pole, north pole, like this. So this, the conductor, ampere conductor per pole. So which means we focus only here, it will be decreased. If let's say one pole, it covers these two parts. But now one pole, it only covers one part here, small part. This is the meaning of an ampere conductor per pole will be decreased. And then, so that the per unit inductance and synchronous reactance decrease. Okay, so per unit inductance, which means it will lead to the L decrease, and also reactance, XL decrease. Because this is a proportional. XL is actually 1 over omega L, right? 1 over, J omega L, something like this. J omega, if not mistaken. So when L decrease, then this will be decreased. Because the area is small, right? And then, this is the thing that it explains, just a statement. Okay, what motor forces, phases. We can build motor with any number of phases, 2, 3, 4, 5. For PM machine, we can build a lot of phases. And then the most common is the 3 phases, because we in our TNB we have single phase or 3 phases. So number of phases influence the required number of power switches to control the winding current. Maybe I'm not sure you still remember your electrical drive or not. If let's say we want to drive a motor, let's say this one is an induction motor with the 3 phases. Okay. Then we need to have a switch. We need to have a switch. Okay, and then we combine all together to become VDC. Okay. After that, we take one phase, connect to one line. Then another one, connect to another line. Then the last one, connect to this line. So let's say for 3 phases, we need about 6 switches. 6 switches, 1, 2, 3, 4, 5, 6, something like this. So at the same time, we may also can see if let's say this is a single phase. And then if let's say we want to run with a MOSFET, okay, basically we only maybe need 2 switches. maybe lah, maybe one like this, maybe one like this, something like this. So this is only 2 switches, but here we have 6. What about more phases? For example, 5 phases. Then maybe we need to have a 10 switch, something like this. Something like this. So number of phases influence the required number of power switches to control the winding current. Impact on the cost as well on the switching losses. So we have 2 things. One is the cost will be higher, switching losses will be higher. Let's say we choose higher phases. And then in your study for this subject, we only focus in the 3 phase. 3 phase will be your basic. And let's say you want to design for more phases, for example, 5 phases, 6 phases, which is now a lot of people want to design a machine. Then we need to prolong it up. So 3 phase permanent magnetic brushless motor. Okay, we have a 1 layer winding, 2 layer 1 and 2 layer winding, which means a single layer and double layer. So 1 layer is something like maybe I'll take this example. Right. One layer. Okay, let's have a try. Right, here got. Okay, 1 layer means for example, let's say this is a 3D. Okay, the motor is like this. Okay, then we wind the red one. So 1 layer means all these occupied by 1 winding, which is go through here. Okay, go through here and then go to the back and then come out, then come out again. It fit all the winding slot, and then we give 2 winding. This is called 1 layer. 1 layer. Okay, another one. Another one. Let's say this is 1 motor. Another one is 2 layer, which means we divide into 2. Okay, so I coil this one to half of it first. Okay, I coil here and then go back, come out, and then it will come out here. Okay, maybe this is 1 coil. Another one, because here got one separated as well, so I coil another one here, go in. Okay, then go to the back, come out like this. So we can see that this is 2 layer. This is called 2 layer. So for A, this is a single layer 1 layer winding, which means it fill out all the slot. It fill out all the slot by one phases. One we call 1 phases. Then 2 layer windings where slot are divided horizontally. 2 layer winding where slot are divided vertically. Just now we talked about is vertically another one is can divide into the horizontal. Horizontal, just now this is a vertical. This is vertical. Okay, double layer vertical. So what is a horizontal? Horizontal, it can be like this, whereby we start divide. We divide like this. And then we have a 1 coil here. Okay, we have a 1 coil. Let's say this is a motor length. So we have a 1 coil. 1 coil slot in, and then it will go until the end, then come out, then maybe slot in the other side here. Okay, then go here and then come out here. Then another one maybe is like this. It's slot in here, and then go in and out here. It will come out like this. Okay, so this is double layer but horizontal, which is mean like this Even though we can see that it's still phase A plus or A minus, for example, this one is fully filled but A plus. This one is a half by half but still A plus, by half but still A plus. But the name calling will be different, which is 1 layer, then another one is 2 layer. And after when we go to the indeed, then we'll see the difference. This one is double layer, which means they divide horizontally So this one is a 5-phase motor, 15 slot. So slot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And 4 poles. 1 pole, 2 pole, 3 pole, 4 pole. So this is interior permanent magnet motor, which means the magnet are inside the rotor iron. You see this one, we still have a rotor iron here. Rotor iron. Double layer winding arrangement, double layer. This is double layer. And then coil spun 2 stator slot. Coil spun is a little bit different. Coil spun is coil spun is actually a name on how we want to wind the motor. This is mean two stator slot, which means for example this one A, okay, it will cross 2 teeth. So when I slot in, when I slot in, then I slot inside, and then I come out here. And then we cross 1 teeth, 2 teeth. This is called 2 stator slot coil spun. For example, if let's say I slot in 1, and then go in, and then go to here, and then go out like this. So I have a 1, it cover this side, it cover 1 teeth, 2 teeth, 3 teeth, the third teeth. So stator tooth, it cover 3 tooth. Then it will be 3 stator slot, or we call coil spun is 3. So another one 5 phase, 15 slot, 4 poles. So still the same double layer coil spun 3. This one coil spun 3. So you see this one is a A, right? Then A mine is here. So 1, 2, 3. So for example, this one is a here, then A mine out. So it's only 1, 2. So another one 5 phase, same, but the coil spun is 4. So you can see 1, A plus, then A minus. Okay, then 1 tooth, 1 teeth, 2 tooth, 3 tooth, 4 tooth. So the coil spun is 4. And for double layer, it must slot like this. No, it must slot go in the bottom. This one is called up, not bottom, top part, and then it come out at the bottom part. It must be like this. It must be like this. When you come to the mini project, you will understand. I mean, you will have this type of question. You have this type of question. So typical power electronic inverter for 3-phase PM brushless motor. This PM brushless motor a little bit stupid. It's not like the fan. When we switch on, it will run itself. We call that one is a line start motor. Induction fan is a line start motor. PM motor cannot. We need to know where is the position of the rotor. So that we need to flip back to the controller. Then the controller will control the switch where they want to fit the line. Okay. So this is the power electronic inverter. Some of the switching is this. Just for your information, that we need a switching waveform to switch it. So sometimes we will use a 3-phase power with modulation, something like this. And then pole, slot, teeth, and yoke. So poles we refer to the rotor poles. Slot we refer to the area where it's filled with the copper wires. So this one is a slot. This one is a slot. We want to fill the copper area. And then bigger slot has a lower winding. But this will adversely reduce the tooth width and the stator yoke, which means if let's say we increase this area, okay, we increase this area become like this, so that this area all are copper slot, winding slot. Then this teeth will be decreased. Okay, this the so-called the tooth width and the stator yoke. Tooth width is this one, the width of the tooth, and then the stator yoke is here. It will be decreased because it will be increased, right? It will be decreased. This is just the explanation, right? Teeth refer to the stator teeth. Number of slot and number of teeth are same. Number of slot and number of teeth are same. For example, we have a slot 1, slot 2, slot 3, 4, 5, 6. So we have a teeth 1, teeth 2, teeth 3, teeth 4, teeth 5, and teeth 6. They are the same. Yoke is a stator yoke and the rotor yoke. Yoke means that the iron on the stator part or rotor part. Stator yoke means the iron on the stator part. This is the stator yoke. This everything here are the stator yoke. And then this everything are the rotor yoke. Rotor yoke. This is one of the hardware, right? For example, this one we have how many slots? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is a 12 slot. So I calculate here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a 12 slot motor. Another one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This one also 12 slot. But this one, the winding is a single layer, which means the whole slot is filled like this. It did not subdivided into two. For example, this one slot, it divided into two. One will go there, one will go here. Cover. For this one, sorry, all teeth are covered by the winding. This one, some of the teeth are not covered by the winding. For example, this is not covered by the winding. So whenever the teeth not covered by the winding, usually it's wasted lah. Usually it's wasted. So that's why non-overlapping. I mean, this double layer will be much better than the single layer. Okay, stated below, motors have a distributed and overlapping winding. Overlapping means it crosses when we slot in here and it come out here. This one is when we slot in. This one when we slot in here, then it go to the back and then slot up like this. Only one teeth. Now this one different many teeth. We go in and then go to the back and then come out. Then again. So this one is called non-overlapping windings. Yeah, this is the possible slot number. For example, if let's say we want to design 3 slot 2-pole machine. Yes, it is possible. Somebody will ask me, hey, doctor, can we design 3 slot, maybe 28 pole like this? This is not possible. This is impossible. So after they come out comparison, this is the possible motor, which I will assign your mini project according to this number. So every group will have a different slot and pole number. So every group will have a different calculation. Mechanical and electrical measure. Okay. So just now what we talked about is more to mechanical side. And then now, because we are studying electrical, right? So how we can interrelated the spatial, because space, geometry-wise, electromagnetism related to spatial, space or spatial. How we can interrelate the spatial to electrical. Okay, spatial usually is something that related to space and we can touch. For example, the mechanical side. Mechanical side. Sorry, I use mouse, so I still don't know what I'm writing. Hopefully you are listening. In electrical motors, two related measures are used for position and speed. Mechanical position or speed is defined as the actual position or speed of the rotor. In one complete revolution, the rotor travels 360 mechanical degrees or 2 pi. Let me use this one. Take this one. See? So we have 2 types of measurement. One, if let's say the rotor is running like this, 1 cycle, we call 360 mechanical degree. Okay. Then another one, where is it? Or 2 pi, or we call as a 2 pi, but in mechanical. Okay. We also have a electrical. We also have electrical. Electrical is something like when we rotate, the motor generate a waveform for us, and then this is the time. And then this one is, if let's say we want to measure something, the x-axis is from here along the circular arc, and it is under mechanical degree. So this is electrical degree or time. We call electrical degree. Electrical degree. For example, the voltage, something like this. And then, where is it? Mechanical position. In one complete resolution, the rotor travels 360 mechanical degree, 2 pi mechanical degree in radians. Having made this revolution, the rotor is right back at where it started. Electrical position is defined such the movement of the rotor by 360 electrical degree or 2 pi electrical degree. So which means in electrical degree, we also have a 360 electrical degree or 2 pi electrical degree. So please don't misunderstanding. They are two different things. But how we want to relate it? This is the position. This is the equation. In order to relate the electrical position, in order to relate the electrical position and mechanical position, okay, we use the formula theta E equals to pole pair times alpha P. So for example, we have a theta M, it's a 20 degree. So this is the number of pole is 2. So our theta E is actually pole pair times theta M. Pole pair means number of pole divided by 2 times theta M, which means 2 divided by 2 times theta M 20 degree. So which is 20 electrical degree. Okay, this one is a number of pole when it is 2. What if number of pole is 4? So theta E, if let's say we want to find the position of theta E when the theta M is 20 degree, so we use 4 divided by 2 times 20, which is 40 degree in electrical. So which means when the motor rotates about 20 degree, the electrical will be at a 40 degree because of the pole pair relationship. Okay, so make sure electrical and mechanical degree are not different. Are different. Then P is the rotomagnetic pole pair or simple pole number. This one is NP and not P. Similarly, the electrical speed omega C and the mechanical speed omega M are the same. So everything when we want to relate electrical to the mechanical, okay, just put a variable and then pole pair times theta M. Or just now we said omega E, right, equals to pole pair times omega M. This is the equation, right? So motor size. How big is the motor that I need to build in order to produce the required torque? So first of all, if let's say we want to design a motor, we need to know what is the power we want to have it. So this is the final. This is the equation, right? This is the equation for cylindrical machines or radial field topology. The output torque can be estimated. Or sometimes, if let's say we some of our senior when he went out to work, and then they feedback to me, how can we start to design a motor? Actually, there are a lot of method and then usually we start from what is the output power we want, and then how good the position the motor size can be allocated. So usually we will use this equation whereby we already know about what is the rotor diameter, what is the axial length, what is the air gap density, and also what is the electrical loading. Then we will give all the things and then to calculate it to find out what is the diameter that we want. So proof. Consider a straight copper wire of length L carrying conductor I in constant magnetic field. So this one is a Fleming left-hand rules where it generates force F equals to BLI. For rotating machine, the output torque is a force times radius. So force is F times radius, which is R. And then for single turn of coil, and then single turn of coil D is a rotor diameter. Where is it? So 2 times I times L times B times R. Oh, directly times twice. Because it's a single turn of coil, which means just now we only consider one cable go in. Okay? If let's say we consider one coil, so which means the cable is, let me draw here. Just now we the torque equals to ILBR, and then this is for one conductor, which means the conductor is go like this only. Okay, then we use this torque. If let's say we want to have a coil, because coil is go in and then go out, like this. For the motor, it go in and go out. So which means the torque will become twice ILBR, which is here. And then we can further derive the number of turns and turns. Turns, which means is if let's say this one is n is 1, so here is 1. If let's say n is n, which means we have 10 turns, and then this will be 10. So or we just slash it and put n. So that's why it's called, if n turn coil, the equation becomes like this. And then 2R is actually the diameter. So let electrical loading, which means we already know about the electrical loading, how the capacity of the motor can run. So we replace Q into the torque equation. Then we found the equation. This is how it proved from Fleming left hand rules. And then all the assumption, then go to the equation. So example, let's say we wish to build a 3-phase PM brushless motor with a 12-stop tempo configuration. Given diameter is a 56, motor axial length 50, Tesla 0.8, 150 turns, and rated 5 What is the output torque? Output torque is actually the power. What is the power of the PM motor? So solution, we need to find the electrical loading. Then we need to estimate torque. And after that, we find out, okay, with this kind of a specification, the torque is about 5 Newton meter. Okay, so I think we finished this one. What about we have a rest for 10 minutes, then we continue again? Okay, now. Do you have any questions?
Okay, sir.
Do you have
No.
any questions? No, we rest for 10 minutes.